We will speed up the flow. Now, the flow velocity outside the boundary layer has increased. At any position along the plate, the boundary layer thickness is now less than before, because with a higher mainstream velocity, the boundary layer has had less time to grow. We have seen the behavior of two-dimensional boundary layers on a flat plate in a uniform velocity field. So far, the pressure gradients in the flow direction have been negligibly small. However, in most flow situations, there are regions of decreasing pressure and regions of increasing pressure in the flow direction. We will examine these two flow situations separately. First, the case of a decreasing pressure or favorable pressure gradient in the flow direction. We will use this 2-to-1 flow contraction and watch the boundary layer along the flat side. The upstream boundary layer is growing slowly as it enters the contraction. After the contraction, the boundary layer is thinner. Note that the distance from the wall to the streamline downstream is about half what it is upstream, because the two-dimensional flow contracts 2-to-1. In the contraction, the effect of the pressure gradient in the boundary layer is to enhance the already high shear stress or vorticity concentration very near the wall. It is as though a new boundary layer were being generated within the old. The combined profile at the exit is relatively thinner because there has been little time for growth of the new boundary layer by viscous diffusion. Using vorticity arguments, we can see that the vorticity added to the boundary layer by the contraction has had little time to diffuse. So downstream, a larger percentage of the total vorticity is nearer the wall. This results in a relatively thinner boundary layer and higher wall shear stress. On the other hand, in a divergent channel, the boundary layer becomes thicker, with a corresponding decrease in wall shear stress. In this case, we have an unfavorable pressure gradient. The increasing pressure associated with a decreasing mainstream velocity decreases the velocity in the boundary layer, so velocity gradients and shear stress are less, and the boundary layer is thicker. At a larger angle, the decrease in velocity is so great that somewhere along the wall, the velocity gradient normal to it becomes zero, accompanied by a local reversal of flow immediately downstream of the point. The fluid, which was in the upstream boundary layer, is no longer in contact with the wall and is separated from it by a region of reversed or recirculating flow. The boundary layer is said to have separated. Point on the wall where the fluid in the upstream boundary layer meets the fluid from the region of flow reversal is called the separation point. The wall shear stress is zero there. Here, the point of separation of the laminar boundary layer is near the first wire. boundary layers we have seen so far have all been laminar. However, in most practical high Reynolds number situations, the boundary layers are not laminar. Rather, they are turbulent. Flow along a cylinder filmed with a high-speed camera can show the stages in the transition of the boundary layer from a laminar one to a turbulent one. A slight adverse pressure gradient causes transition to occur within the field of view. The steps in the transition are very complicated and interdependent. Of nearly two-dimensional waves, the Thomaine-Schlichting waves, followed by the appearance and growth of three-dimensional disturbances associated with streamwise vorticity. Then turbulent spots can be seen. And finally, fully turbulent flow appears. Here, the exact position where growth of two-dimensional disturbances begins depends on random small-scale fluctuations in the flow, and therefore varies with time in a random way. This boundary layer around a channel bend is made turbulent by placing an obstruction in the layer upstream. The obstruction stimulates the naturally occurring processes and hastens the onset of transition. The flow here is all downstream. Removing the trip rod results in separation and backflow. Bubbles accumulate at the separation point. In this diffuser, which was used before, we have made the bottom boundary layer turbulent by inserting a trip rod upstream. The turbulent boundary layer is able to withstand the adverse pressure gradient in the diffuser, while the laminar layer along the top wall is separated, allowing reverse flow. These timelines show that in the turbulent boundary layer, there is no separation. The overall flow is downstream. To see why a turbulent boundary layer can withstand a larger unfavorable pressure gradient without separating, we shall again examine the flow along a flat plate. The boundary layer on the bottom side is laminar and two-dimensional. On the top side, the boundary layer has been tripped by a wire placed well upstream. Unsteady motions in the turbulent boundary layer are three-dimensional. Some of the motions are perpendicular to the plane of view. These timelines correspond closely to the instantaneous velocity profiles for the two types of boundary layers. Superimposing a number of displacement lines enables us to obtain a mean velocity profile for the turbulent layer and the laminar layer, and at the same time gives an experimental notion as to where the fluctuations occur and how large they are in the plane.